An electrocardiogram, also called ECG or EKG, is a measurement of the electrical activity of the myocardial cells, and it gives a direct measurement of the rate and rhythm of the heart. So an ECG measures the magnitude and the direction of the wave of electrical activity through the heart. There are electrodes placed on the skin that measure small potential differences on the surface of the body that reflect the activity of the heart. And it's possible to measure the electrical activity of the heart with these electrodes that are so far away from it, because the summed electrical fields generated by waves of depolarization and repolarization are large enough to be detected even with these electrodes that are placed on the skin. So first, let's look at this grid of the ECG. And there are lots of these little tiny boxes, and each one is 1 millimeter square. So 1 millimeter by 1 millimeter. Groups of these smaller boxes make up these larger boxes that are delineated by these darker red lines. And the darker red lines are 5 millimeter square boxes. So time is being measured on the horizontal axis, and each small box corresponds to 40 milliseconds, which means that each 5 millimeter large box corresponds to 200 milliseconds, or 0.2 seconds, which is a fifth of a second. So 5 of these large boxes make up 1 second. The vertical axis is calibrated to 0.1 millivolts per millimeter, and this shows the strength of the wave of electrical activity. So if one small box is equal to 0.1 millivolts, that means each large 5 millimeter box is equal to 0.5 millivolts. Now let's look at the waves that are recorded on an electrocardiogram. So remember that the entire myocardium isn't depolarized all at once. The atria depolarize first, then the ventricles depolarize in a specific sequence, and the atria repolarize at that same time, and then finally the ventricles repolarize. So this sequence and timing of this spread of depolarization and repolarization is important. And it's detected and recorded, and under normal circumstances looks something like these waves here. So the signal's made up of 3 main parts: the P wave, the QRS complex, and the T wave. The P wave is this small, usually positive wave right before the QRS complex, and it corresponds to atrial depolarization. So this is when the wave of depolarization that spreads from the SA node throughout the atria is occurring, and the length of this P wave corresponds with conduction time through the atria. This large QRS complex is made up of multiple parts, and it corresponds to ventricular depolarization. So the Q wave is this initial negative wave, the R wave is the first positive wave, and the S wave is the negative wave that follows that R wave. So together, this QRS complex represents depolarization of those ventricles, and even though the ventricles are relatively large, they depolarize rather quickly, and that's because of the fast conduction velocity of the His-Purkinje system. Then the T wave follows the QRS complex, and it corresponds to ventricular repolarization. Now, let's think for a minute about how these waves correlate to the action potentials that are occurring in cardiac myocytes. So, atrial depolarization would correspond to an action potential in an atrial cell. So, the P wave would correspond to phase 0 of an atrial action potential, and then that phase 3 repolarization of an atrial action potential would be hidden here during this QRS complex. So this just gives you a rough idea of what's happening with the action potential. The relationship between the QRS complex and the T wave and action potentials in ventricular cells is that the QRS complex corresponds to the phase 0 depolarization of the ventricular action potential. That time in between the QRS complex and the T wave corresponds to that phase 2 plateau phase, and the T wave corresponds to phase 3, or ventricular repolarization. The time duration of specific portions of an ECG can tell us a lot about the spread of the depolarization. So first, let's look at intervals. And intervals are sections that include a portion of a wave. So we have a PR interval, a QRS interval, and a QT interval. So the PR interval is measured from the beginning of the P wave to the beginning of the QRS complex. And this interval designates the time between the start of the atrial depolarization and the start of the ventricular depolarization. It tells us if the electrical signal is making its way from the SA node and all the way through the atria and through the AV node and into the ventricles as it should. The QRS interval is this relatively short interval, and it's measured from the beginning to the end of the QRS complex. And that QRS interval corresponds to ventricular depolarization. So this could tell us if the spread of depolarization through the ventricles is happening in a normal pattern and at a normal rate. And finally, the QT interval. This QT interval is measured from the beginning of the QRS complex all the way to the end of the T wave, and it gives us the time of the overall ventricular action potential. And that is the time that it takes for the ventricular depolarization, mechanical contraction of the ventricles, and finally ventricular repolarization. So this tells us about the spread of those action potentials all throughout the ventricular muscle and whether it's happening in a coordinated and physiological manner. So we just saw intervals that have portions of a wave. So now let's look at ECG segments. And these segments are the time periods that are in between waves, and they don't include portions of the wave themselves. The PR segment is the time between the atrial depolarization, when all the atrial depolarization has ended, and the beginning of the ventricular depolarization. Most of the time in this PR segment is the time that the depolarization is making its way through the AV node. So this segment results from the delay of cardiac excitation during that slow propagation through the AV node, and it reflects that time delay between atrial and ventricular activation. The ST segment tells us how long the ventricular myocytes are in that plateau phase. And remember, in the plateau phase, this is the time when the ventricles are in between depolarization and repolarization.